Required practicals come up every single year for GCSE Physics. In this video, I'm going to talk you through all the ones you need to know for AQA Paper 1. So those include insulation, specific heat capacity, resistance of a wire, current voltage characteristics, and density. The first one, insulation, is a separate science-only one, so I'm going to leave that till the end. For each of these practicals, we're going to talk through a 6-mark method that will be a perfect for a 6-mark answer. We're going to talk through the independent, dependent and control variables, any graphs you could be expected to draw, the accuracy or how it can be improved for different practicals, and also things like safety and what if there was some slightly different equipment or different method to what you've revised. And the first one we're going to start with is specific heat capacity.
Why is it that different substances take different amounts of time to increase in temperature, even if they're heated for the same amount of time? Well, the answer lies in something called specific heat capacity and how much energy they can store. So before we dive into the practical, which is one of the harder ones in paper 1 physics, let's look at the definition, because it's worth 2 marks if you can recall this in an exam. So specific heat capacity is the energy needed to increase the temperature of 1 kilogram of a substance by 1 degree Celsius. It's 2 marks because there's quite a lot to remember, but there is a hint and there is a tip. If you manage to look at the equation for specific heat capacity in your exam. Now, it depends on this thing's specific heat capacity. It depends on the mass of the substance, so how much there is. It depends on the energy supplied, and as a result, the temperature will increase. So how much will the temperature increase by could all help us work out the specific heat capacity. Now, putting those factors all in one equation, this equation given to you, obviously, the E should be obvious is energy in joules, M is mass in kilograms, C stands for capacity or specific heat capacity, and this little delta triangle thing here means change, and the theta, the symbol, is temperature. So that's one to remember because it's quite tricky. Now, if you know the units for the other 3 things, which are relatively straightforward, you should be able to figure out the units for specific heat capacity. If you can rearrange the equation, it's energy in joules divided by mass kilograms, and then temperature in degrees. So it's one of those units you can figure out if you get stuck in the exam. Now, what it means, and you might be able to ask to apply this into an exam, is that it means a higher specific heat capacity is able to store more heat energy without a large increase in temperature. So essentially, if it doesn't increase in temperature that much, it has a higher specific heat capacity. And a lower specific heat capacity means it doesn't take much heat for its temperature to increase. Right, let's have a look at an example then. So imagine you put a bowl of food in the microwave. Some of it is going to heat up more than others because they're made of different substances with different specific heat capacities. On to the practical. So you've probably done this in class. You will have a block, usually of metal. It can be done different ways. It could be oil, could be a liquid. But either way, you'll have a substance you're trying to measure the specific heat capacity for. You'll have a heater, usually called an immersion heater, just a fancy name for a heater you put in. And you'll have a power supply to power the heater, and you'll have a joule meter. More on that in a second. To measure the temperature, you're going to need a thermometer, obviously. You will also need a balance or some weighing scales, which I haven't drawn here, but are really important. So the first step, and you can keep an eye on the equation to check you're getting everything down. First step is to measure the mass of the metal or whatever you're using a balance. Next step is to put your thermometer in and measure the initial temperature using a thermometer, and obviously write it down. Make sure you mention all your equipment here. Now the next step is when we start really switching things on and getting the practical started. So it says turn the heater on and place in the metal block, and then you're going to start a stopwatch. Now stopwatch time we're going to come on to later. Obviously time isn't in our equation, but it will be important when we graph this. Then once you started the stopwatch, you're going to record the temperature every 2 minutes, could be 1 minute, could be 30 seconds, could be 5 minutes, whatever the question asks you to do, and record the energy change on the joule meter at the same time. So the temperature and the joule meter, 2 things to record here. Next, what we're going to do is after, let's say, 10 minutes, we can use the equation. So I've rearranged it here for specific heat capacity, energy divided by mass times by temperature change to calculate the specific heat capacity. Now, sometimes questions can be really tricky and they don't give you a joule meter to measure energy. In that case, you'd need an ammeter to measure the current, and you need a voltmeter, which I've not drawn very well here, but across the heater to measure the potential difference. If you multiply those 2 values together, that gets you the power of the heater, But we don't need power, we need energy. So there's another equation involving power, which is energy is equal to power multiplied by the time, which is why we're using a stopwatch. Okay, so do keep an eye on that. It'd be very mean if that came up in an exam, but it could happen if you don't have a joule meter. Okay, what kind of results could you be expected to talk about then? So if you measure the temperature over time, you should find a graph that looks a little bit like this. Now, it's not directly proportional, and there will normally be a bit of a horizontal section. The reason for that is because there's time taken for the heater to heat up, basically. The heater will be cold initially until you plug it in, so it will take some time for the heater to heat up. The gradient of the straight part of the line is equal to the change in temperature divided by the change in time. Now, we haven't got time in our equation, so this again is one of the hardest things they could ask you about this practical, is if they ask you to use the change in temperature divided by time, then the energy is no longer the energy, it's the power, because power equals energy divided by time. So sometimes they might ask you to work out the power, you use the gradient, multiply by mass and specific heat capacity. They could also ask you to plot energy versus temperature, but the graph will look the same. Safety for this practical, kind of an obvious one, don't touch the heater, wait for it to cool down before you put it away and before you touch it at all. Errors or inaccuracies, there is always going to be energy lost to the surroundings, so you want to make sure you're using insulation around the block to reduce that. Even with really good insulation, that will always be an inaccuracy in this practical though. So use insulation or a lid to reduce this and improve your accuracy. If you don't do this, the energy you supply will be bigger than the energy heating the block. And that will mean that the specific heat capacity value you get will also be bigger than it should be. As with most things using a thermometer, you're also going to have parallax error as well if you're not reading it at eye level. This required practical is all about how the resistance of a wire changes with length. So we're going to change the length, that's our independent variable. We are going to measure our dependent variable, the resistance of a wire. Now the resistance we can't calculate directly, but we need to be able to use an equation. So it happens to be the potential difference divided by the current if we rearrange V equals I times R. Now we might be asked to label the circuit diagram or draw the circuit diagram. So we need a cell or a power source, a voltmeter, an ammeter, and a wire. A wire doesn't really have a symbol, so we just draw a squiggly line. Let's have a look at the method. So first part is to place crocodile clips, as in the little image there, and a wire in line with a meter ruler. Okay, now in line is important so we can measure it properly, more on that later. And then we're going to connect to the wire 20 centimeters apart. That's going to be what we start on. If they give you different results to give a method for, you have to say whatever length that is, but 20 centimeters is a good start. Next, we're going to be really explicit and mention our equipment. We're going to measure the current using an ammeter. We're going to measure potential difference using a voltmeter. Nice easy marks there. Then find the resistance using the equation I mentioned earlier. Resistance equals potential difference divided by current. That's how we find the resistance with those two measurements. Next, what we're going to do is we are going to vary the length of wire. That's our independent variable. So we increase the distance between, increase the length by moving crocodile clips by 10 centimeters. So 30, 40, 50, etc. Then record the new potential difference and current readings. Then we're going to repeat. So you don't have to mention exactly the range you go up to, but let's say it goes 20, 30, 40, you go up 20, 30, 40. If it says 30, 50, 70, you mention 30, 50, 70. You want a range of values. Now with your results, you could be asked to plot a graph, or I'll be given a graph of length versus resistance. Now those two variables should be directly proportional, meaning if there's no length, there's no resistance. It should go through the origin. Now, while we're here, it's a good explanation, a good idea to explain why this occurs. So if you imagine electrons going through a wire, if it's twice as long, for example, then essentially the electrons are going to have more collisions between them and the ions. Therefore, more collisions means more resistance. So a longer wire means a greater resistance and shorter wire means a lower resistance. Now, let's have a look at what kind of questions you can have about errors in this practical. So the main one to look at is you need to make sure to make it accurate, you disconnect the voltmeter or the cell, beg your pardon, between readings to avoid the wire getting hot. So if the wire gets hot, the resistance increases, which we don't want to happen. That's an external factor. We want to keep that the same. You can also have parallax error if you're not reading the ruler in line. So what that means is if you were these people here, and ignore my terrible drawings of eyes, imagine you're trying to measure an object from one side and your mate's trying to do it from the other side. If you're not in line with the ruler, perpendicular to it, you're going to have different readings. Safety, it's kind of an obvious one here. You've got a bare wire, don't touch it. Not that it will electrocute you because you're using a low voltage, but it may get hot. And to avoid it getting hot in the first place, okay, you want to make sure you disconnect it between readings, or you could even pause the experiment. It will reduce the potential difference if it continually gets too hot. Now, different variations of this practical exist where you could be asked to find the resistance of a network of resistors. It's the same method, voltmeter, ammeter, PD divided by current, but this time the independent variable might be the number of resistors. So just be aware of that. A characteristic of something just means a property or how it behaves. So current voltage characteristic of a component just means how does the current and the voltage, or PD, vary for individual components. Now you need to know the circuit diagram. It looks a bit like this. You need an ammeter, you need a voltmeter, and you need what's called a variable resistor. So an ammeter measures the current, a voltmeter measures the potential difference or voltage, same thing, and the variable resistor is the thing I guarantee you'll forget, which changes the resistance and therefore changes the current in the circuit. We'll come on to a bit later why that's so important. Now, the components you could be asked to talk about, there are three of them, okay? So you could be asked to talk about a fixed resistor, that's the rectangle with a box. The rectangle, that's a fixed resistor. The circle with a cross in it you could be asked about is a filament bulb or lamp, and the third one is a diode, or could be a light emitting diode. It would be the same thing in this context. So the method's the same for all three. Let's have a look at what we could be asked to write down. So first things first is we're going to talk about the experiment, and we're going to talk about the circuit we've got. So we're going to measure the current using the ammeter and measure the PD using the voltmeter. That should be nice easy marks straight up. Next, what we're going to do is, this is where the variable resistor comes in. Okay, so we're going to use the variable resistor to change the resistance. Now, the reason why we want to do this is because we want to get a range of values for current and PD. So we'll come on to what the graphs could be in a second, but the reason is we want a range of values. So then the ammeter and voltmeter readings will change. So we're going to record the new values of current and PD using the ammeter and the voltmeter. Now, we should have a range of values, so we're going to repeat that last step or two to make sure that we are going to have a few different values. And the last step is the most important step. Again, one that you want to make sure you don't miss out because you can't get full marks without it. We are then going to reverse the connections on the cell. So flip over the positive, negative, negative to positive to obtain negative values for the current and PD. Okay, so it's important we know in the negative direction what the current and PD are. Now, the reason for that is because the graph you're going to be asked to plot for these experiments is a little bit different. You notice how this is different to a normal scientific graph. Instead of just having kind of the x and y axis going from the origin, it has them flowing in the positive and the negative direction. So you do need to know what these graphs look like, not just for this practical, but generally. Now, a fixed resistor, the graph of PD and current is a straight line that goes straight through the origin. So that special name called for that is directly proportional, a straight line through the origin. So what that means is, if you're just given the results as one variable, i.e. the PD, doubles, the other variable, the current, also doubles straight through the origin. This is what's known as Ohm's law, is that voltage is proportional to current. Now, for the filament bulb, it is not directly proportional. It curves off a bit at each end. Notice it doesn't curve downwards, the current. It looks like this. The reason for this is because as for a bulb, the temperature increases, so resistance increases. So what that means is the current will stop increasing at a certain point. Now, the reason that the resistance increases with increasing temperature is that when ions are hotter, there are more collisions between electrons and ions. Therefore, more collisions means resistance goes up and current stops increasing. Now, the last one, if you put a diode in there, is that current only flows in one direction. In the negative direction, there is zero current. In the positive direction, there is a current that increases. Now, that's because in one direction, it's a low resistance, in the other direction, it's a very high resistance. So there's not that many errors or safety issues with this practical, but you could mention about disconnecting between readings to stop the wires getting hot. So if the wires got too hot in this case, or the voltage was too high, means there's some extra resistance which you don't want. Electrical safety, this applies for all electrical practicals really. Please don't say, I don't know, don't get electrocuted, things like that. That's not going to get you marks. You'd say things like don't use frayed or broken wires, or report them to your teacher. And maybe don't use water near your experiment, things like that. So that would apply for all electrical practicals. Density is required as the mass divided by the volume. So all we need to do for this practical is measure those two things practically, and then we've got an answer for our density. So let's look for a regular solid first. So that will be a cuboid or a cylinder, but realistically it's going to be a cube or a cuboid. To find the mass, we place the object on a balance. Now, balance comes up in mark schemes. I wouldn't say scale, because scale could be a scale of anything, or measuring scales is fine. I prefer balance. So that's the easy bit. Next, to measure the height and the length and the width of the object, we are going to use a ruler. Please make sure you include your equipment. Okay, it's an obvious one, but ruler. To find the volume, you then multiply those three lengths together. So the volume of any cuboid is just the length, height, and width multiplied together. Then use the equation to find the density. So we'd mention the equation again, even though it's given to you, mass divided by volume, and then sometimes you're asked to compare it to a value for that material and find out what material it is. An irregular solid is a bit trickier. Now, by irregular solid, I mean anything that's not a regular cuboid or sphere or cylinder, anything like that. So it could be, I don't know, a piece of metal, a screw, a statue, anything like that. Now, the first step is exactly the same. To measure the mass, we are going to place it on a balance. Same as before. To measure the volume is a bit trickier. There's a couple of sub-steps here. So to measure the volume, we can't measure the length, width, and height because it's not a regular shaped object. So we're going to use one of these. This is called either a displacement can or a eureka can. So essentially what we do is you fill the eureka, or sometimes called the displacement can, to just below the spout with water. Now, that bit's really important, we'll come on to later. Then you're going to slowly lower the object into the displacement can, and you're going to collect the water from the spout in a measuring cylinder. Really important, this bit. A measuring cylinder just below the spout to collect all the different drops of water that come out once you put the object in. Now, the reading or the amount of water that's in the measuring cylinder is the volume. Okay, so the volume of water, measuring cylinder measures volume. That's the only way to get the volume. Once you've done that, same step is the last step is the same as before. You're just going to do the mass divided by volume to find the density. Now, you could be asked to find the density of a liquid, okay, which is even easier than the first one, I would say, because first of all, you're going to put your beaker on a scale, on a balance, beg your pardon, measuring scales or a balance. Then, instead of measuring the mass this time, what you're going to do is you're going to zero it, essentially. So make the mass zero when there's a beaker on it. Now, the reason for that will be clear in a second. So it measures zero. Then you're going to pour in whatever liquid you're measuring. And then the new mass, so what the reading is now, equals the mass of the liquid. Okay, so you haven't had to do any subtracting, you just zero the start, and that becomes easier. The volume you can measure using the little gradients and the scale on the side of the beaker, or you could use a measuring cylinder, then just use the equation mass divided by volume to find the density of that liquid. Okay, so you do need to know all three, but there are similarities between them. So different errors then you could encounter during this experiment. We're going to deal with the irregular solid because that's by far the most errors you can have. So the issue might be that when you lower it in, water splashes when lowered, or if you don't fill the spout fully. That could lead to the volume you measure, the water that comes out, being lower. So it could be a lower volume, which means that the density you record might actually be a bit higher. You could also have, when measuring the mass of the solid or liquid, a zero error on the balance. You could also have something called a parallax error, only for the solid, regular solid, when you're reading using a ruler, or with the measuring cylinder when you are reading the volume. Okay, check out my other video if you're not sure what a parallax error is. Why is it that puffer jackets keep you so warm in the winter? Well, it's all to do with their insulation. How would you know the best material to use? Let's find out how we go about doing that. So for this practical, there's a couple of things you could use as your independent variable. One of them is the insulating material, but you have to read the question carefully to figure out if it's the material or if it's the number of layers, and if it is material, what exact materials are you using? So for an example, I've got 4 beakers here. We're going to wrap one of them in cardboard, one of them in bubble wrap. I'm going to wrap one of them in sand, which sounds weird, but I'll talk about it later, and I'm going to wrap one in cotton wool. You could also have one without any insulation as well. The dependent variable is going to be the same regardless of the material. What you're measuring is the temperature decrease. Control variables in this case would be the same volume of water we are going to put in each beaker. We're going to use, if we're using the same thickness of material, that means it's a different material each time, and we're going to have the same starting temperature. So like I said, we're going to fill them all with water from a kettle, nice hot water, make sure it's hot enough to start with to allow us to figure out how much it decreases by. So for the method itself, what we're going to do is wrap the same thickness of material or different materials around, let's say, 4 beakers. If there are 6 beakers in the question, then you talk about 6. If there are 8, you talk about 8. But it's a really good idea to get your control variables into your method so you don't forget to write them down later. Once you've got them all set up, and that's important to do that first, you're going to pour in boiling water from a kettle or a boiled kettle, and it's going to be, again, the same volume for each beaker. So how would you know that? Well, the beaker will have markings on it, so you can determine whether it's the same volume or not. Next, what you're going to do is you're going to measure the initial, or the temperature at the start. So the initial temperature for each beaker, and we're going to say what we're going to use. We're going to use a thermometer. Now, you can do one after the other, but all at the same time makes your life easier, less to mention in your method. Then you're going to use a stopwatch or a stop clock, and you're going to start it, and then you're going to time the experiment, and you're going to record the temperature every, let's say, 2 minutes. It could be 30 seconds, it could be 5 minutes, depends on what the question asks you. Now, how do you go about knowing which material was the best insulator? You could be asked to plot a bar graph, or be given a bar graph to determine which one is the best, or it could be a line graph. So for a bar graph, and sorry for the shoddy drawing on this, they would give you, let's say, the 4 materials on the x-axis, and on the y-axis might be the temperature decrease. So in this case, the material that has the highest temperature decrease is the worst insulator. Another graph they could give you, which is a little bit trickier, is a line graph, and each material would be a separate line. So it'd be a bit meaner than to give you 4 of these, but they could do. So let's say one has a very low temperature decrease over time, one has a bit higher, one has somewhere in the middle, and one has quite a high temperature decrease over time. And actually, one of them, you can see here, the red one would be the worst insulator because it has the highest temperature decrease over the period you're measuring for. It actually goes down all the way to room temperature. Blue in this case would be the best insulator because instead of having the highest temperature decrease, it decreases by the lowest amount. Okay. Now room temperature, if they do ever stop decreasing, it'll stop at about 20 degrees because that's the temperature rooms are commonly at. Now, for a bar chart, like I said, the worst insulator would be the highest bar, and the best insulator would be the lowest bar, which I know is different colours here, but I'm just doing it to show you what's there. Now, it's really careful you read the question carefully because there could be variance here. Instead of doing different materials, they could give you one material in a question, and you're asked to change the thickness of the cardboard. So instead of having 4 different materials, it would say something like, 2 layers of cardboard, 4 layers of cardboard, 6, 8, 20, 100, doesn't matter. You've got to be able to look at the question and figure out how to adapt your method. So for the graph, it would be slightly different. You'd have a bar chart of 2, 4, 6 different layers. But look how much the method is the same. There's one major change, which is instead of wrapping the beakers in different materials, you'd say wrap the beakers in different numbers of layers of cardboard. So you'd say 2, 4, 6, 8. Be specific as you can. Now, the only thing that changes, apart from that, is just that method 1, okay? Now, you'd have a different graph, but it would be very, very, very similar in your conclusions. Safety with this practical, please don't say things like don't touch the water. You don't need to touch the water, it's not on your method, but to make sure you don't spill it, we use things like a funnel to pour the boiling water, or you could say keep beakers in the center of the table to make sure you're preventing any burns and breakages, things like that. If you're pouring the hot water, you could also say use goggles, but that wouldn't be the major risk in this practical, I don't think. Now, because this practical is relatively straightforward, there's only like 3 or 4 steps, they'll love to ask you about different errors that might occur. So one thing that can reduce accuracy is if heat is escaping from each beaker. So you'd say keep a lid on to reduce heat escaping. That would mean more of the heat is being kept and distributed via the insulation. You could then say use the thermometer. When you use it, give it time to settle for each beaker. So maybe give it a few seconds to rise to where it's going to rise to, rather than just doing it straight away. There's also, when you're talking about thermometers, always parallax error, which means you're not reading it at eye level. So ensure you read it perpendicular to the thermometer to make sure you get an accurate reading.
And that's the end of required practicals for paper 1 for AQA GCSE Physics. If you want some exam question practice on any of these, please click the video here, and I've done a couple of walkthroughs for each practical, which you will find really useful. Thanks for watching.